Okay, so we have an isoparametric mapping for the geometry. Right, so that says that, as we know very well now, x think I sub e, right, as a function of c vector is again obtained as a sum over the nodes NA, right, and now NA we know is a function of, is parameterized by the coordinates in this bi-unit domain, and we have here x a I e, right. This is exactly the same as before. Okay, and once we have this, we know what other use we can put it to, right? Do you remember what else we do with this? Right, we use it to write out our gradients, right? So for gradients, and what are the gradients we need? When we look back at our finite dimensional weak form, we already see this, that sort of gradient, right? WHI comma J, right? This now over the element is sum over A, NA comma J, C A I E, right? I'll probably add an E in there as well, okay, just to keep decorating it, right? And of course the same thing for U, H, I comma J. All right, UHI comma J is over element E is again sum over A, NA comma J, D A I E. Okay, and we know straight away where we expect to use this, right? Of course, this shows up directly in the weak form when we look at it, right? Just recall the term on the left-hand side in our weak form, integral over omega WHI comma J. We have sigma H, but we know, of course, that sigma H is just C I J K L. Okay, sigma I J C I J K L epsilon H K L. Okay, but here is where I'm going to use one of those properties of our elasticity tensor. And the property I'm going to use here is the fact that whereas the strain is properly defined as the symmetric part of the displacement gradient, right, that's the strain. However, because we've talked about how the elasticity tensor is possessed of minor symmetry in those two indices, we are actually completely free to not worry about the symmetrization of the displacement gradient in using this constitutive relation. Okay, so what I'm saying is that we are completely correct long as we make sure that C has minor symmetry. We are completely correct in writing this asCijkl U K comma L. Okay, and the reason for this is minor symmetry. Okay, All right. And if you're wondering, yes, it is indeed, of course, true that for that term also, whereas I've just written it as a gradient of the weighting function, we would be right if we were to go the other way there and say that it's the symmetric part of the gradient of the weighting function. All right, but we just don't need it. We can leave it this way. So minor symmetry with respect to the ij indices, which we also have, takes care of things for us. Okay, but at any rate, we see clearly what gradients we need to compute, right? You should remember that k and l here are, of course, just dummy indices because they're being summed away, right? Or even otherwise, they would be dummy indices. And so when I say I'm going to compute i comma j here, it's really the same thing. All right. So we do need to compute gradients. But once we have our isoparametric mapping, we know how to go about that as well, right? And what we're saying here now is that NA comma J is just NA comma C capital I, right? Using as before the uppercase index for coordinates in the bi-unit domain. We have this times derivative of Ci with respect to xj, right, for all j, as before. Well, it's 1, 2, 3 really. Okay, and of course we know how to compute this now, right, using the Jacobian of the mapping, right? So what we do here is use the Jacobian of the mapping. Right? And that, when we write it out as a matrix, is the following, right? J, right, depending upon the coordinates in the bi-unit domain, is, we know this all very well now, x1 comma c1, x1 comma c2, x1 comma c3. We go on until we come down here and we get x3 comma c3. Right? But then, of course, we also know that J inverse of C is C1 comma x1 until C3, sorry, 1 comma x3, and we go on until we come to C3 comma x3. Okay, and once again, because we have only a 3 by 3 to invert here, it's actually not that hard to do it analytically, right? So in our element formulations, as I suggested before, for the scalar problems, we could do this analytically, right? So we thereby get each of these derivatives that we need, right? And therefore we know how to compute the gradients. Okay, well, if we know how to compute the gradients, we can go ahead and assemble our problem, right? Our weak form. We'll do that in the next segment. We'll end this segment here.